last lecture of module 5, I am going to do a very pertinent example of the use of solutions of differential equations. Okay. And this is an example from quantum mechanics. You will see this in your elementary quantum mechanics course. Okay. But what I want to do today is to work out a problem that you see in your elementary quantum mechanics course and highlight where we use lot of our knowledge of differential equations in this problem. Okay. And the problem that I will be taking is the solution of the Schrodinger equation for the hydrogen atom. The hydrogen atom has one electron and one nucleus. Okay. The nucleus is considered fixed. Okay. And you can write the Schrodinger equation for the electron in terms of the wave function of the electron. Okay. So now I can show this is the wave function for the electron in a hydrogen atom. Okay. The first term is the kinetic energy term. Okay. So the wave function is psi. I have written it in terms of the coordinates of the electron, and the electron coordinates are written in spherical polar coordinates. Okay. So the first term is the kinetic energy, and it has a Laplacian operator. So, the gradient square operator. Okay. And now the next term is the potential energy term, and this is written in terms of this constant 1 over 4 pi epsilon E square. E is the charge on the electron and the nucleus, and over R multiplied by the wave function, and this should be equal to some constant E, okay, which is the eigenvalue of the energy times psi. So you can immediately see there are lots of aspects. So you see vector calculus in terms of gradient operator, you see spherical polar coordinates, we see some elements of eigenvalue problem, not in terms of matrices, but in terms of differential equations. You see second order ODE, actually it is a PDE, okay, which when we solve it we will see techniques of second order ODE, and in particular we will see power series method. Okay. So, all these aspects, all these mathematical aspects will be seen as you work out this problem. Okay. So, all these various mathematical aspects will be seen when in this problem, and that is the reason I want to really highlight this problem. Now, let us start. So we will be using a technique. Okay. So, this is a partial differential equation, it is a function of r theta phi. Okay. So, we will assume separation of variables to solve for psi of r theta phi. So what we will write is psi of r theta phi as a product of three functions, one is a function only of r, the other is only a function of theta, and the third is only a function of phi. Okay. So, I have just used r, s and t. Incidentally, this term, this theta phi term, is sometimes combined in books with the symbol y of theta phi, and this is something called spherical harmonics. Okay, this is something called spherical harmonics, but we will not bother with this much here. Okay. Now, the Laplacian, the square Laplacian that appears in this equation, okay, it has to be written in spherical polar coordinates, and you will get all these terms. Okay. So now one of the things, before we go to solve this equation, okay, we see all these constants h, 2me, 4 pi epsilon, e square, all these constants. So what we will do is we will use what are called atomic units, and we will set all these constants to 1. So what happens is the differential equation in atomic units, it looks much nicer. Okay, del square psi, okay, minus 1 by r psi equal to E psi. Okay, so I mean these two equations are essentially the same, only all these constants I have removed them. If you want, you can keep the constants, but then the expressions become more tedious. So it is essentially the same equation without those constants. So what we will do is we will work with this equation, okay, and now we will start applying the various methods. So before we apply the methods, let me say a few things what our overall strategy is going to be. So I will just explain the overall strategy of this solution. Okay. So what we are going to do is we are going to take this equation. Okay. So we are going to use 3 steps. First step is separation of variables. This is a technique that you will learn more formally when you are dealing partial differential equations, but this is a very common technique. Okay. So separation of variables to get, and what will give you is 3 ODEs for r, theta and phi. So where 3 ODEs, in one of them the independent variable will be r, and in the other the independent variable will be theta, and in the third the independent variable will be phi. Okay. So we will get 3 ODEs, that is what we are going to do. Okay. Then we can easily, I'll write it here. So solving for T phi is easy. So this can be easily done. Okay. So now then you solve for T phi. So solve and substitute and put in equation for s theta. Okay. Then solve for s theta. Now this involves power series method. And the third and the last step is to solve for r of r. This also involves the power series method. In particular, this involves something called the associated Legendre polynomials. And this involves something called the associated Legendre polynomials. Okay. So I haven't explained you what these Legendre polynomials are, okay, but through this at least I will do the Legendre polynomials in detail. Okay. The Legendre polynomials we'll leave it as an exercise. So okay. So these are the 4 steps. Okay, and we are going to go through these steps one by one in solving this solving this partial differential equation. Okay, so let's get to the first step. Okay, so the first step is the separation of variables. Okay, so let me do this. So separation of variables. So our differential equation was 1 over 2. Now you had del square. Now del square has this long expression. Okay, so it is dou square by dou r square psi, okay, plus 2 by r dou by dou r of psi plus 1 over r square sin theta dou by dou theta of sin theta dou psi by dou theta, okay, dou by dou theta of this whole thing. Okay, plus 1 over r square sin square theta dou square psi by dou phi square minus psi by r is equal to E psi. So now this differential equation, what we see is that if you substitute the expression for psi, okay, so psi is equal to r of r, s of theta, t of phi. So if you substitute this expression, okay, then whenever you have a derivative with respect to r, it will only operate on the r coordinate. So the s and theta can be taken outside. Okay. So I will substitute and so substitute and divide the entire equation, divide both sides by psi. Okay. So, psi is r times s times t. Okay. So, let us look at the first term. So, when I substitute, so what I will get is I will have the minus half. Okay. Now, when I take a d square by dr square, so what will happen is I will get s t times dou square r by dou r square. Okay. That will be this first term. Okay. And you know, you will get all the other terms. Okay. But what will happen is when I divide by psi, then I will divide this by psi. So, when I divide s t by psi, I will just get 1 over r. So, what will happen is it will just become 1 over r. So, s t divided by psi, psi is r times s times t. So, I will just get 1 over r. Okay. Now, the next term will become 2 by r r dou r by dou r plus, now what I will get is 1 over r square sin theta. Now, I will have s of theta and dou by dou theta of sin theta dou s by dou theta, because here the d by d theta will only act on the s term, plus I will get 1 over r square sin square theta dou square t by dou phi square, and I will have a t. Okay. And now, the next term will just be minus 1 over r equal to E. So, now what we see is that the right hand side is a constant, it is independent of r, theta and phi. So, this constant is independent of r, theta, phi. This term is purely a function of r. This is only or a function only of r, only of r. Now, at the same time we can also see that I will put it in green. So, if you see this term, this is a function only of theta, this term and theta. Okay. This term is function only of phi. Okay. So, this is a function only of phi. Okay. So, what you see is that if you again all this is this whole thing is function only of r. So, I want so I think what I want to say is fairly obvious. Okay. So we have a left hand side that has one term that is a function only of r, the second term that has a function of r multiplied by a function only of theta, third term has a function of r that is r square, function of theta that is sin square theta, and a function that is only a function of phi, and then you have another term that is also a function only of r. Okay. So what you can say is that if this whole thing has to give a function which is a constant, okay, then you can immediately say that all the terms that is only a function of r, okay, or the term that is only a function of phi, okay, there should be no dependence on phi on this equation. So immediately you can say that d square t by d phi square 1 by t dou square t by dou phi square is a constant. Okay, so that is the first thing you can say, okay, because this is the only term that depends on phi and nowhere else do you have phi in the whole expression. Okay, so this has to be a constant, there should be no dependence of phi on the equation. For convenience, let us call this constant as m square. We will take it as m square. Okay. For now, let us just start with this. Okay. There is an understanding of why this should be a positive constant, but we will not bother with that right now. So this is the equation for phi. Now we are into the second we are into the second step of the solution, that is solving for t phi is easy. So this is an equation. I should be a little careful when I write these should really be whole derivatives. Now when I write, because r is only a function of r, okay, so these are actually not partial derivatives because t is only dependent on phi. So this I can write as 1 over t d square t by d phi square. So all these derivatives of s with respect to theta is a d by d theta because there is only a theta dependence. Okay, so all these derivatives become regular derivatives. Now let us go to the next step, that is solving for phi. You have d square t by d phi square is equal to m square t. Okay, so this implies t is equal to e to the I. This constant I will set as minus m square. Okay, I am sorry, I want to set this as minus m square. So with this we will come to it later why this constant should be negative, okay, but we will set this constant as minus m square. So if we set it as minus m square, you can immediately see that t should be e to the I m phi. So t of phi is e to the I m phi multiplied by some constant a. Okay, so the a is a normalization constant. So now phi varies from 0 to 2 pi. So this gives t is equal to 1 by root 2 pi e to the I m phi. M has to be an integer. Okay, now why does m have to be an integer? Okay, because you should have t of phi is equal to t of phi plus 2 pi. So phi should satisfy this condition. So this implies, okay, so t of phi is 1 over root 2 pi e to the I m phi. This should be equal to 1 over root 2 pi e to the I m phi times e to the I m 2 pi. Okay. So if these two have to be equal, okay, then you can immediately see that you can cancel these and you get the condition e to the I m 2 pi equal to 1. Now e to the 2 pi I is just 1. Okay. So you get m has to be an integer, m equal to 0, plus minus 1, plus minus 2, etc. So and this normalization constant of 1 by 2 pi is 1 by root 2 pi is there to satisfy. Okay, so this constant comes from integral t star t d phi from 0 to 2 pi. Okay, this should be equal to 1. This is the normalization condition for this wave function. Okay, so t star t equal to 1. Okay, so therefore now t star is just e to the I m phi. Okay, and you can clearly see that this a has to be equal to 1 by root 2 pi. So this completes the solution for phi. Okay, now what we do is we take this solution. So we use this form of t in this equation. Okay, and we write the remaining part of the equation. So let us write the remaining part of the equation. Okay, and what I will do is I will collect the r terms together, okay, so that you can see the expression. So let me write the remaining part of the equation. So I will get minus half. Now let me write in terms of d square r by d r square times 1 by r plus 2 by r dr by dr, and I have a minus 1 by r. So these are all the terms that depend only on r. Then I have the other term, that is 1 over r square sin theta, okay, and then I have an s d by d theta of sin theta ds by d theta, okay, and then I have a 1 over r square sine square theta. What I had was I had d square t by d phi square and 1 over t, okay, but that is just equal to minus m square. So, what we said is that 1 over t d square t by d phi square is just minus m square. So, I will just substitute minus m square. So, what I will minus half. So, we had the minus half, and what I have here is I have minus m square, okay, equal to E. So, this is the next expression, and what we want to do is to solve this for theta. Okay. Now, you can see again what you can see that the same trick that we had earlier can be used, okay, because what we see is that this is the only part that depends on theta. These two are the only terms that contain theta, okay, and so whatever you have the theta dependence here, okay, that should actually be a constant, okay. So what we will do is multiply by r square. By r square. So, if you multiply this whole thing by r square, okay, then what you will see is that the part that depends on theta is just contained in this term, okay, and that should be a constant, okay. So what you will get is that you will get minus half, and I will just put an r square, and you have a 1 by r d square r by dr square plus 2 r by r dr by dr minus r, okay, and then you have a minus half, and now what you have is something that depends only on theta. D by d theta of sin theta ds by d theta minus m square by sin square theta equal to E times r square. Okay. So, the right hand side is only depends on r, okay. Left hand side has one term that depends only on r, second term that depends only on theta, okay. So, this has to be a constant, okay. So therefore, we can immediately say that 1 over sin theta s d by d theta of sin theta ds by d theta minus m square by sin square theta, okay, this is a constant. So, the next thing that we want to do is to actually solve this equation, okay. So, that will be the next part. So, the next part is this is the equation for theta, for s, this is second order ODE for s of theta, okay, and this is what we want to solve, okay. So, this is the third step of this problem, okay, that is to solve for s of theta, and it turns out that this is a slightly more complicated solution, okay. So this is what we are going to do next. So, the next step is to solve the second order ODE for theta. So, what we have seen is that we have a differential equation for theta, and now what we want to do is to go ahead and solve this. Now, this will be solved using the power series method, okay, but before solving using the power series method, we will make a couple of small we will make one substitution of variables, okay, one change of variables. What we will do is we will let cos theta equal to x, okay, and s of theta we will write this as p of x, okay. So, s of theta is p of x. So, if you change the variable, then the function will have a slightly different form. So, we will just call it p of x. So, with this substitution, you can substitute in this differential equation, and you can take the appropriate derivatives, okay, and then what you will get is you will get a differential equation that has this form 1 minus x square, okay, I will write p double prime of x, double prime means second derivative with respect to x, okay, minus 2 x p prime of x, and let me call this constant as beta. Okay, so, I will call this constant as minus beta. So, then this will become plus beta minus m square over 1 minus x square times p of x. So, sin square theta is 1 minus cos square theta. So, that is how you get this, and you will get a differential equation like this, and this equal to 0. Okay. And you can immediately see that this is a homogeneous second order differential equation, okay, in p of x, okay, and we will solve this using the power series method. Now you can solve this for a general value of m, okay, you can solve this for an arbitrary value of m, okay, but it turns out to be a little more involved. Okay. So, we will take the case of, consider the case where m equal to 0. Okay. So, when m equal to 0, then this differential equation has this form p double prime of x minus 2 x p prime of x plus alpha p of x equal to 0, or sorry, plus beta. What we are going to do is we are going to let beta equal to alpha times alpha plus 1. Okay, you can always do this, you can always write beta in this form. Okay, so, alpha is beta is some real number, alpha is also a real number. So, if you let this form, then what you get is called the Legendre differential equation. This turns out to be a very famous differential equation in engineering, okay, that was discovered many centuries ago. Okay, 1 minus s square p double prime of x minus 2 x p prime of x plus alpha plus 1 p of x equal to 0. Now, this equation, as I said, is a very famous differential equation, and this has been solved nearly 200 years ago. So, let us look at how we can solve this differential equation, okay, and what we will do is we will apply the power series method at this point. Okay. So, the power series method will be applied only when the differential equation is in this form. Okay. So, what we will say is let p of x is equal to sum over a n x raised to n. Okay. Yes, and I forgot one thing. So, n equal to 0 to infinity. Before we do this, okay, we can see that that x equal to cos theta. Okay. So, therefore, minus 1 less than equal to x less than equal to 1. Okay. Now, for x not equal to plus minus 1, okay, this is a regular then all points. So, all points are regular. Okay. So, any point except x equal to plus minus 1 is a regular point. Okay. So, that means that means where we are interested, that is minus 1 to 1, except at the boundaries, all the points are regular points and they are not singular points. Okay. So, we can write the differential equation solution, we can write the solution in this form as an ordinary power series without the x raised to r term. Okay. So, now you can do this and you can substitute for p prime of x and p double prime of x, and I will just write the write the expression. So, I have 1 times p double prime of x. So, I will write that as sum over n equal to 0 to infinity, okay, and I have n minus 1 a n x raised to n minus 2. Okay. Now, I have x square. So, minus sum over n equal to 0 to infinity n minus 1 a n x raised to n minus 2 into x square, that is x raised to n. Okay. And then I have minus 2 x into p prime. So, p prime will give me n times, so I write minus 2 sum over n equal to 0 to infinity Now, I have n a n x raised to, I had x raised to n minus 1 because of p prime. Okay. Now, it will become multiplied by x will give me x raised to n, okay. And then I have plus alpha alpha plus 1 sum over n equal to 0 to infinity a n x raised to n equal to 0. So, now this is the expression with which you start, and now let us try to compare it term by term. Okay, this is the most this is the first step in the power series method of solution. Now, what we will do is compare term by term. So let us say x raised to 0 terms. So, on the left hand side, if you want x raised to 0, then n has to be equal to 2. Okay. So, if you want a term that has x raised to 0, then n has to be equal to 2. So, you have 2 into 1 into a n. So, you have 2 a n, okay, that is the first term. In this term, if you want x raised to 0, okay, then n has to be 0, but if n is 0, this n into n times n minus 1 is 0. So, you do not have any term with x raised to 0 here. Similarly, if you want x raised to 0, then n has to be 0 in the third term. Okay, n has to 0 n being 0 means the third term goes to 0, and then you have plus alpha alpha plus 1 a 0 equal to 0. Okay, so here n equal to 0, you have a 0. Oh, I should n equal to 2. So, there should be 2 a 2. Okay. So, this is what the term looks like, and so what you get is that a 2 is equal to minus alpha alpha plus 1 by 2 a 0. Okay. Now, we can go ahead. What about x raised to 1 terms? Okay. Now, what you will get if you want x raised to 1 in this, then n has to be equal to 3. So, you have 3 into 2, that is 6, and a 3. So, you have 6 a 3. Okay. In this case, if you want then in the second expression n has to be 1, but if n is equal to 1, then n times n minus 1 goes to 0. So, you do not have any n equal to 1 term here. The third term will give you again if you have to have n equal x raised n has to be equal to 1. So, you get a 1. So, you have minus 2 a 1. And in the last term you will get plus alpha alpha plus 1 times a 1. This has to be equal to 0. So, all the terms, because right hand side has no x raised to 1 term. Okay. So, plus 1. So, what you get a 3 is equal to minus a 1 times minus a 1 times. Okay. Now, what you have is alpha alpha plus 1 minus 2 divided by 6. Okay. So, I have chosen to write it in this form. Okay. But basically a 3 is related to a 1. So, a 2 is related to a 0, a 3 is related to a 1. Okay. Now, suppose you consider a general, let us say x raised to n terms, or x raised to, let me call it x raised to m terms, okay, just to distinguish from that variable. So, if you look at all terms that have x raised to m, okay, so if you want to have x raised to m, then what you should have is in this should be n should be equal to m plus 2. So, you have m plus 2 m plus 1 a m plus 2 minus, if you want x raised to m, okay, so x raised to m, of course, we are saying m is greater than 2. So, m greater than equal to 2. Okay. So, then in this case you will have if you want x raised to m, then you should have you should have m m minus 1 a m minus 2 m a m plus alpha alpha plus 1 a m equal to 0. Okay. Now, what you see is you have a m plus 2 and you have a m. So, what I can do is I can write a m plus 2 is equal to a m times some quantity. Now, the denominator is m plus 1 m plus 2. Now, what I have in the numerator, okay, so I have m minus 1 plus 2 m. So, that is so what I have is m minus 1 plus 2 m minus alpha alpha plus 1. Okay. So, what this looks like is m times m plus 1 minus alpha times alpha plus 1 divided by m plus 1 m plus 2 times a m. Okay. So, this is called the recursion relation. This is called the recursion relation. And notice this is a recursion relation of this differential equation, of the Legendre differential equation. So, we had the Legendre differential equation, we made this substitution, okay, and then what we noticed was that when we make this, when we use the power series method, we get a recursion relation that relates the coefficients. Okay. So, notice that when you have the power series method, what your goal is to determine these coefficients a n. Okay. Now, what we saw was that we can write a 2 as something times a 0, a 3 as something times a 1, and you can write any m plus 2th term in terms of a m. For m greater than or equal to 2, you can write the m plus 2th term in terms of a m. Okay. Notice that m plus 2th term does not involve a m plus 1. Okay. You can write it distinctly in terms of a 2. So, what that means is that if I write a 4, I can write as a 4, that means m equal to 2. So, 2 into 3, that is 6 minus alpha plus 1 divided by 2 plus 3 into 4, that is 12 a 2. I can write a 5 equal to, so 5 means m equal to 3. So, m equal to 3. So, 3 into 4, that is 12 minus alpha plus 1 divided by 3 plus 1, 4 into 5, 20 a 3. Okay. And what you can do a few more things. Okay. So, if you look at a 4, I can write as 6 minus alpha plus 1 divided by 12. Now, for a 2, I can use my expression for a 2 and I can write as minus alpha plus 1 by 2. So, I will write this as 0 minus alpha plus 1 divided by 2 times a 0. Okay. And I can write a 5 as 12 minus alpha plus 1 divided by 20 times, now for a 3 I use this expression that I had before. So, I will write this as 2 minus alpha plus 1 by 6, 2 minus alpha plus 1 by 6 times a 1. Okay. So, what this implies is that all even terms, okay, even terms coefficients can be written in terms of a 0 and all odd terms coefficients can be written in terms of A1. Okay. So what our power series will look like? So, I can write the power series in this form. So, P of x looks like this. So, A0 times sum over only the even terms. So, I will just write n even, okay, and what I will get is a n by a 0 x raised to n plus. So, a n by a 0 is some number that depends on alpha, okay, and I have a 1 times sum over n odd a n by a 1 x raised to n. Okay, so, this contains only odd terms, this is even terms only. And what is important is that these are not, these are just functions of these are just functions of alpha. Okay. So, I can use, I can write this as so this is a general solution. If you think of a0 and a1 as a0 a1 as arbitrary constants, then this represents a general solution of this equation. So, this is a general solution. Okay. Now, the general solution has two linearly independent solutions. So, the polynomial the series with only even terms and the series with only odd terms are linearly independent. So, this is a general solution that is written in terms of a linear combination of these two solutions. Okay. Now, let us consider the case, okay, let us go back here. Okay. So, now suppose alpha is an integer. Alpha is an integer, let us say equal to L, okay. Then a L plus 2 equal to, you can see from this expression. So, when you look at a L plus 2, you will get L plus 1 minus alpha plus 1 is just L plus 1. So, a L plus 2 equal to 0, and because a L plus 2 equal to 0, a L plus 4, a L plus 6, all these equal to 0. So, that implies that series terminates at n equal to L. Okay. So, one of the series, terminates at n equal to L. Okay. This terminated series is called a Legendre polynomial. Of degree L. Okay. So, what you get is, this is represented as P L, or L is put in the subscript, P L of x, okay, is a polynomial in x of degree L. Okay. And P L of x is one solution. Okay. So, it is one solution. So, basically if L is even, okay, then P L of x is equal to a 0 plus a 2 x square plus a 3 x a 4 x 4 plus dot up to a L x raised to L. If L is odd, actually this is written slightly differently. Okay, so PL is, I will say, proportional to this. Okay, I will just say it is proportional to this. If this is odd, PL of x is proportional to A1 plus A3 A1x plus A3 x cube plus A5 x5 plus dot dot up to AL x raised to L. Okay, with some constants of proportionality, this is what your Legendre polynomials are. Okay. Now, we can go ahead and you can write lot of properties of Legendre polynomials. So many properties of Legendre polynomials. Okay, but basically now I will just you can read from various books. Okay, we won't I won't be spending too much time on that. Okay, rather what I will just write is that finally what you will get is your S of theta is proportional to. Okay, now PL of m of cos theta. Okay. Now, PL of m. Okay, so remember we considered m equal to 0. Okay, so this is associated Legendre polynomial. From all, and this comes when m is not equal to 0. Okay. Now, now I've actually it turns out that that if when you have something like this, when you have two series, okay, and alpha is an integer, then one of these series will terminate. Okay, and as I said, A0 and A1 are arbitrary constants. So what is done is you take the series that terminates. Okay, you use that as the required solution. The other solution you can throw away from conditions on the wave function. Okay, so we use only the solution, only the polynomial solution that which shows which is due to the terminating series. Okay, so now what you get is you have the associated Legendre polynomial that appears naturally in this equation. I haven't done the m not equal to 0 case. Okay, needs more work to solve, which I have not done to solve. Okay, but you can look up again in standard books. Okay, so now when you do this, okay, what we will get is that this whole thing, when you use this solution and you put back in the differential equation for theta, okay, what will happen is that this whole factor, okay, so this whole factor of will just be replaced by L plus 1. Okay, and then you will get an equation. Okay, so substituting for S of theta, okay, we get an ODE for R and for actually R of R. So the ODE for R has this form. So I will just write minus 1 by 2 d by dr of R square dr by dr plus L plus 1 divided by 2 R minus 1 by R minus E times R equal to 0. Okay. Now, you can expand this and you can clearly see that this is a second order ODE in R. Okay. And this is actually the solution is solved using Frobenius method. Okay. But you know, before that, after a substitution. Okay. So, you first make a substitution and then you solve using Frobenius method. Okay. So, so I won't do this explicitly. Okay. So, this you can refer books, refer standard books. Okay. So, so this is done in Macquarie. Macquarie has it, and Macquarie Mathematical Methods, that is second edition, has this topic. Also it is also there in standard quantum mechanics books, quantum chemistry books. So, I will conclude this module here. Okay. So, what I have tried to show in this module is the techniques to solve second order differential equations, and I have just given you a very brief and very quick overview of the techniques. Okay. Now, these are techniques that you can learn. So, with this background you can actually work out all these, and you can actually show how to use all these techniques to solve second order ODEs. Okay. So, I will conclude this module here. Thank you.